Okay, so welcome everybody to the first scientific session of this conference. I'm very pleased to have Valentina Rosso as our first speaker today. She is from LPTMS in Orsay, and she's my nearest neighbor in Orsay. Our office is just next door. So Valentina, she's going to talk about what is your topic? Out of equilibrium activated dynamics in glassy systems, landscape approach.
Exactly. So thanks a lot, Satya, and thanks also to all the organizers of this nice meeting. So I'm very happy to be here. It's also my first time in Bangalore, so thanks for this chance to be part of this very nice workshop. Okay, so the talk of the topic that I'd like to tell you about today is based on joint work that we have been doing with Alessandro Pacco, who is a PhD student in our lab, the LPTMS in Orsay, and Alberto Rosso, whom you have met just before. And the idea is to look at out-of-equilibrium dynamics, in this case of a classical system that has some glassy features. And what we are interested in here is low temperature dynamics of these systems and a particular regime of this time evolution that is known as the activated regime. So I'll give you an outline of the talk in a minute, but before let me clarify what is the setting that we have in mind in here. So as I mentioned, we are interested in classical dynamics. So think about some system which is described by some configuration vector, which I will call S in the following. And the system evolves with an equation of motion of this form. So a configuration change following some first term here, which describes essentially gradient descent in some energy landscape. So you want to optimize the energy function associated to the system. And then you have noise, which here we take in the form of the usual Gaussian white noise. So this is a Gaussian process with equal time correlations, which are proportional to something that I will call a temperature. And we are interested in these dynamics in two particular limits. So the first one is that of high dimensionality. So the configuration space to which this vector belongs has a dimensionality capital N that I assume to be very large in the following. And moreover, we are interested in the case in which the noise is weak, so temperature is small. Now, when I say that we want to look at these dynamics in systems which are glassy, what I mean is that the energy landscape that appears in this gradient term is glassy in the sense that it is rugged, so it looks a bit like this. It's a landscape which has a lot of local minima that I will call metastable states, but also in general a lot of stationary points, so this could be minima, maxima, saddles of this function, which are essentially attractors of my dynamics in absence of the noise. So if you had no noise, you know that the dynamics would want to reach this type of configurations. If you add a little bit of noise, you still expect that this stationary point will play somehow a relevant role in your dynamics. And when I say that there is a lot, what I mean is that the number of this special configuration has a scaling with the dimension of configuration space, which is exponential. So it's the same scaling as the total number of configurations of your system. So you really have a landscape that is very non-convex. And the coefficient here, which controls this exponential scaling, is what we call a landscape complexity. Now, one very natural way to generate landscapes which have a positive complexity is by introducing randomness, essentially, in your system. So this is what I will do in the following. I will consider situations in which this energy function is a random function defined on configuration space with a given statistics that is, for simplicity, we will take to be Gaussian. Okay, so let me tell you what we do in this work, and then I will essentially spend the rest of the talk trying to motivate why we do this calculation and what this has to do with this activated regime of the dynamics. So what we compute essentially is what I call here a conditional entropy. So it's essentially a counting problem where what we want to count is the number of triplets of metastable states. So think about local minima of these complicated landscapes. This is what I call here S0, S1, and S2. And we want to count them as a function of their properties. So this means that we want to fix their energy density, which are parameters of our choice. And we also want to fix their geometrical configuration, so the distances between these points in this underlying very large configuration space. And to be slightly more precise, the object that we actually compute is this function here, which I call a 3-point complexity, which is a function related to this number n. So this number n is a random variable because my landscape is random. And it counts essentially the number of configurations as 2. So let's say the third element of my triplets. And S2 has to be a stationary point. It has a given energy density of our choice, and it is conditioned to be at fixed distance from another pair of configurations, S0 and S1, which themselves have a conditioning in the energy density and on their mutual distance, B01. So in this sense, I call this a conditional entropy. We're actually counting the number of configuration S2 under the conditioning on the other two. And what I will do in the following is essentially discussing why, as I mentioned, we want to compute this quantity. So I will give no details on what is the structure of the calculation behind this. The methods that we use are what are called nowadays in the literature replicated Katzreis formalism. Technically is a combination of techniques that one uses when dealing with statistics of random functions, which are standard in the field of Glasses, like replica formalism. And there's also quite a lot of randometrics theory behind this, but I will not go into that. But of course, if anybody's interested, I will be very happy to discuss this. And you may have a look at this review where we mention a little bit the structure of the calculation of this type of problems. Okay, so this is the goal. And now in the rest of the talk, what I will do in the first part is essentially to tell you what is the model for which we do this calculation. So I will specify my energy function. And I'll try to motivate why this is a good model for Glasses. So what is the history of this model, why people think that it is relevant when studying dynamics of Glassy systems. And I will then mention why this problem of activity dynamics is still an open problem in this context. And then in the second part, I will give you the results of our calculation and motivate it from the point of view of the dynamics. Okay, so let me begin from the model. The model is actually pretty simple to write down. It is what in this literature of Glasses is known as the pure spherical PSP model, but you can really think of this as being just a Gaussian function, a Gaussian field that you define on a high-dimensional hypersphere. So this means that my configuration space will be now an hypersphere in large dimension n. So my configuration vectors will satisfy this spherical constraint. And the energy is defined like this. So to each configuration, to each point on the sphere, I associate a value of the energy, which I get summing over all possible p-body interaction terms, which I can build out of the components of this vector S. So p here is an integer of your choice. It has to be larger or equal to 3, but it's a parameter. And this sum has coefficients, which are random variables with Gaussian statistics. So they are IID for each choice of the indices, and they have a given variance. So in my notation here, the variance is 1, and I scale everything in such a way that this field is extensive. So it scales with n. And this is a model that has a pretty long history. So it was introduced already in the 80s with the purpose of understanding physics of Glassy systems. But I also wanted to mention that somehow, if you look at the literature in more recent days, you will see that this model emerges actually in a variety of contexts which are not directly related to Glasses, and also which seem quite unrelated to each other. So let me just give a few examples. So you have problems of high-dimensional inference or denoising, where you have essentially, for example, tensors that have a deterministic component plus a random term, and you want to get rid of the random term, which represents the noise. And in general, you can map these type of problems in some sort of optimization problems for energy landscapes of this form. And we have been working on this, and here is an example of this. You can quantize the model, and then it becomes interesting in this context if you want to study violations of eigenstate thermalization hypothesis and clustering of the Hilbert space. This is another example here. It's a model that nowadays people are also looking at in the context of holography. And there may be in the audience people that work on SYK, so you will recognize that the structure is very similar, except that for SYK you have fermionic variables, and here I just have real numbers. And moreover, very recently there is a lot of work which is related to understanding and modeling theory of learning, so in the context of machine learning, for example. And this model emerges there in different forms. So both if you're interested in supervised learning, so when you have to train networks, but also in the context of generative models. And again, this is an example which comes from the field of generative models. So there is quite a lot of interest in understanding features of these high-dimensional Gaussian landscapes. Now, coming back to Glasses, why is this, let's say, a good model? And in particular, why is this a good mean field model for glassy systems, which I think may look a little bit surprising, because in general, when you think about glasses, so these are physical systems, they are made of particles, so if you have to figure out what is a good mean field model for these systems, you may think about models of particles, so where your degrees of freedom are particles, which interact to each other, and that you study in some mean field limit, which corresponds essentially to the infinite dimensional limit. And in fact, these type of models have been solved in the literature, but they have been solved pretty recently, so I would say in the last 10 years or so. And the mathematics, the theoretical construct, which is behind this type of theory, is actually quite non-trivial. But it's very worth in the sense that from this type of analysis, you can extract really a lot of predictions which are quantitative on both dynamics and static properties of these glassy systems. And these are predictions which in some cases go well beyond the mean field limit. So let me just show you an example. So these are critical exponents for, let's say, in this case, an equilibrium transition that you have in the context of glasses. You see that they are very non-trivial exponents, which you derive in mean field. And these are simulations down to 3 dimensions. So, I mean, it's a theory that can be relevant well beyond mean field. However, if you're interested in some aspects of this theory, and in particular for what concerns dynamics, it was realized much before these recent 10 years that simple models which are extremely abstract, like the one that I just mentioned, the spherical p-spin, actually are able to capture already this type of phenomenology. And these are models which I think are very interesting for theorists, because they are models for which the dynamics in the mean field limit, so the mean field limit for my spherical p-spin means that I'm taking n, which is the size of configuration space, to infinity. So the dynamics in this limit is explicitly solvable. And the solution is non-trivial, so it captures really phenomenology of out of equilibrium, such as the occurrence of aging, that are pretty interesting and that you find then when looking at models of interacting particles. So let me summarize a little bit this phenomenology. So I'm mostly interested in dynamics. So one very standard way to study dynamics, which everybody here is very familiar with, is by means of quenches. So here I have a classical system, so a quench for me would be essentially a quench in temperature, which means that I take my system, I prepare it in an initial condition that is, let's say, at equilibrium at some very high temperature, say infinite temperature. So this is just a random configuration on my sphere. And then I run my Langevin dynamics with a noise which is associated to a temperature which is much smaller. And the question that I ask is whether under these dynamics, the system equilibrates at the temperature associated to the noise. So equilibration means several things, but one necessary condition is that if I look at one point function in times, so for example, at the behavior of the energy, I find that this converges to some stationary value, and this stationary value is precisely the one that is predicted by thermodynamics at the temperature associated to the noise. Now, I do this exercise for my spherical p-spin, and what I see is that there is a special temperature that I call TD, this stands for dynamics, where a transition occurs. So if I quench above this TD, everything works well and my system thermalizes. Whereas if I try to equilibrate below TD, I see that the system in mean field is not able to reach this equilibration. It goes out of equilibrium, and it has all these interesting dynamics with aging phenomenology. So aging essentially means that the dynamics of my system becomes slower and slower as time evolution proceeds. So relaxation timescales of my system grow with the age of the system, basically. And you may wonder, well, okay, I have a dynamical transition. Does it correspond to some thermodynamic transition, which is underlying? And you find that this is not the case here. So this is a system where you do have a thermodynamic transition between a paramagnet and a glass phase, but this happens at a temperature which is different from the one of the dynamics and which is smaller. So what's going on at this transition that is purely dynamical? And which is relevant because it captures somehow the phenomenology of these glass-forming systems, like supercool liquid, that have a temperature where you see that relaxation timescales essentially grow by order of magnitudes. So this is a lot is in log scale, and you see that in a small interval of temperature, I have a huge shooting up of, in this case, viscosity of these materials. Now, what's going on? You can, I told you that this has a solvable dynamics, so let's see what this solution tells you. So having a solvable dynamics in this context means that this is a system for which you can derive exact equations of motion, which we call the MFT, for, let's say, dynamical quantities, which are essentially 1 or 2 point function in times. So you see here correlation functions or the profile of the energy density. There are also response functions, which are hidden in here, which are essentially order parameters of your dynamical theory. So in the limit n going to infinity, you can derive such equations which are exact and which are closed in these quantities. They look like this. And this involves no approximation, so there is no closure scheme that you need to implement to derive these equations. And these equations, of course, you can solve them numerically, so these are integral differential equations, but you can also find really ansatz which solve, so let's say you can guess what is the functional form for these objects that if you plug it into this equation, they solve the equation in the limit of large times. Of course, limit of large times, which you take after taking n going to infinity. That is the first limit in this formalism that you need to take to derive the equations themselves. So you have such ansatz, and what this ansatz is telling you is precisely that there is this dynamical transition, and it tells you much more. So it tells you not only that the system goes out of equilibrium, but it tells you how the system goes out of equilibrium, so you can really characterize this type of aging that I mentioned before. And there are a lot of, so here is a lot of keywords that now we associate very naturally to Glassy dynamics, but whose, let's say, understanding and derivation emerge precisely through the solution of this simple toy model. Okay, this is a comment for quantum people, but I will skip it. And if anybody's interested, I will mention that it's connected to some things that people working on quantum disorder systems also know quite well. Anyway, so this tells you, okay, I have this dynamical transition and I can characterize how the dynamics goes out of equilibrium, but you may still wonder what happens, so why the transition happens at this temperature. Can I understand it more precisely? And the way you understand it is going back to the structure of the energy landscape associated to your dynamics. And what you can do here is to do some sort of topological analysis, so you can count what is the number of stationary points, so of configuration which satisfy this condition here, as a function of the energy densities. So you scan your landscape as a function of the energy and you count how many metastable states or in general stationary points I have at that particular energy. And if you do this, you realize that there is a special energy, which is the energy that corresponds to the dynamical temperature. So it's the energy of equilibrium at the temperature where you have your dynamical transition, where you have what people call a topological transition in the structure of the energy landscape. So this means that if you look at the landscape above this special energy, you count these stationary points and you realize that all the stationary points up here are, they are exponentially many, first of all, but they are all saddles. So they are stationary points which are unstable dynamically. So you look at the landscape around and you find that the curvature of your landscape has many directions where it is negative. So your gradient term will allow you to move along these directions and to move away from the corresponding stationary point. On the other hand, if you look below this threshold, you find that there you have exponentially many stationary points which are truly local minima. And these local minima are isolated in configuration space and they are separated by very high barriers. So the energy barrier that you have to cross to go from one to another one is, in this model, it's extensive in the size of configuration space. And these are the configuration which are, let's say, dangerous for your dynamics in the sense that they are really able to attract the dynamics and trap the dynamics for very large times. And so you understand why you are going out of equilibrium. So you are doing your quench, you start from very high energy, you ask to your system to equilibrate at a temperature that corresponds to an energy which is below the threshold, and the system will not do it in its mean field dynamics because it will be able to descend in this landscape in the upper part where you have all these saddles, but then exactly at the threshold, it will start to meet these metastable states, and there it will be essentially stuck, it will go out of equilibrium, and you have the dynamical transition. Okay, so this is all well understood, but as I stressed, this is well understood in mean field. So you need to take n going to infinity and then to study the dynamics at large times. So you may wonder what happens to this dynamical transition if I now try to go beyond mean field. And going beyond mean field means that you take in your system n, which is the size of configuration space, to be, let's say, possibly very large, but finite. And what happens is that this transition in this limit becomes essentially a crossover, and it becomes a crossover because you have activated events. So events in which your system is able now to jump from metastable state to metastable state, crossing these high energy barriers. Now, crossing these energy barriers requires that you use the noise somehow to counteract the gradient and climb up in this energy landscape. And this is a process which is very rare. So think about Arrhenius scaling, your temperature is very small. So the typical timescales that you expect for this type of transition will be exponential in the barrier. The barrier here scales with n, so these type of jumps occur at timescales which are exponentially large in n. So if you send n to infinity, you're pushing away all these processes and you don't see them essentially in the mean field treatment. So understanding this type of, let's say, physics of activated processes is actually an open problem in this field. So one would like to get a theory, at least in the context of this toy model, which is as good as the theory that we have for mean field dynamics. And this is quite challenging. It's a little bit like doing, let's say, when you have a double well problem in quantum systems and you try to do, or you have escape processes in classical systems. But the problem is that you have a geometry that is very complicated. So it's not just two wells, but it is exponentially many wells that you can explore. So this geometrical complexity adds to the complexity of the description, dynamical description of these escape processes, which is itself already challenging because it requires you to go beyond the mean field approximation. Okay, so this is what we would like to say something about. So now let me go back to our geometrical analysis. So what are we trying to do here? So of course, we are not solving this problem of activation, but we try to somehow figure out something about these dynamics through an analysis of the geometry of this random function. So let me try to explain the logic. So the idea is that you want to now describe these very rare processes where you are at the bottom of this energy landscape and you want to jump from metastable state to metastable state. Now, instead of looking at the full Langevin dynamics, let me try to simplify it. So of course, there are huge separation of timescales here. So there will be there will be huge time windows where my system will be in one metastable state and fluctuate within, and I'm not interested in this. And then there will be these jumps from metastable state to metastable state. So let me try to describe these dynamics in a coarse-grained way, where I just figure out what are these states, and I just try to describe the jumps between them, associating some transition rates to each activated path, which will be, in general, the product of the transition rate associated to each of these jumps. Now, I don't know how to compute these transition rates, so this is a complicated path integral that I don't know how to quantify at n finite. But I can do some assumptions. So first, I can assume that these transition rates depend on the configurations only through parameters, such as the energy densities, and the distances between these configurations in configuration space, which here I parameterize with the overlap. So remember that configuration space is a sphere, so distance between vectors is just parameterized in terms of the scalar product between them, which is a very natural assumption to do for these Gaussian landscapes, because the landscape has a statistics which is isotropic, so everything statistically should depend on quantity which are essentially rotational invariant. And then what I also do is to focus on a subset of activated path where every time that I jump, I decide what is the energy where I want to jump. So for example, I start from S0. I decide that I want to jump to a point which has energy epsilon1. And I choose among the exponentially many metastable states which I have at my disposal in the landscape, I always choose the ones which are closer to me in configuration space. So the ones which maximize the overlap between the configuration that I reach and the one that I'm starting from. So in this way, my transition rates essentially are parameterized by the energy densities and by these overlaps which are obtained through some maximization process over the full population of metastable states, which are surrounding the first one in configuration space. And now the question that we ask is, can we understand how much correlation propagate along this path? And we kind of have in mind two possible scenarios. So the first one is what we call avalanche-like scenario, and this is motivated by the study of low temperature dynamics, which is activated for systems which are a bit different. So they are in finite dimension and they still have randomness, but they are, for example, of the form of elastic manifolds in random potentials. So if you look at the dynamics of these systems, what you realize is that activated dynamics has these avalanches in the sense that every time you have one activated event, then this tends to be followed by a sequence of other events which are somehow facilitated by the fact that you have done one jump before in your dynamics. So we try to mimic or translate this phenomenology in this inequality, which is telling us that the rate which is associated to my second jump is higher because I know that I'm coming from a first jump. So let's say the second jump is facilitated by the presence of the first jump, which means that it is higher than the rate that I would get, forgetting about the fact that I'm coming from a previous configuration, and this is essentially the rate that I would get if I had started my dynamics directly at the configuration S1 without knowledge that I'm coming from a previous jump along my path. And on the other hand, you can have, let's say, a competing scenario where instead the dynamics is memoryless and you have no information of the previous rate, or this information doesn't matter when computing the rates. And this, so I will go very fast on this, but this second assumption of memoryless dynamics is somehow what is hidden in most of these toy models that you find in the literature for activated processes in high dimensions. So perhaps some people in the audience are familiar with Bouchot-like trap models. They always assume that the dynamics is memoryless. Okay, so the idea is that we have in here is essentially to translate this condition about the rates into a condition about the distances between these metastable states in configuration space. So within the assumption that I mentioned, you can show that this situation is realized whenever the maximal overlap between these two configurations, knowing that I have a third configuration as 0 in my vicinity, is larger than the maximal overlap that I would get statistically in my landscape if I looked only at the pair S1 and S2, forgetting about the fact that I'm conditioning to be in the vicinity of S0. And on the other hand, the second equality corresponds to an equality between these overlaps. So now we have mapped this into a geometrical problem, and now we can use the quantity that I mentioned to characterize precisely these distances. So I mentioned before that we compute this conditional distribution which is related to triplets of points, and this contains all the information that we need. So now I'm showing you just an example of how this function looks like. I'm fixing here energy densities, I'm fixing my parameter Q, and I'm showing the log of the number of configuration S2, which I have in my landscape, as a function of these other overlaps Q0 and Q1. And what we're interested in for the dynamics is the maximal value of Q1, where we start seeing stationary points there, local minima in this case. And this precisely coincides with this point in here. And for this value of parameter, we can show that this point is exactly the same that we would get from a calculation where, if you want, from a two-point function where I do not have the configuration as 0, but I only look at distances between S1 and S2 without any further conditioning. So this points toward this memoryless-like scenario of the dynamics. But it's not the only thing that you see in this type of landscapes. So if I change a bit the parameters, I see also instances where instead this maximal overlap predicted by the two-point function is strictly smaller than the one predicted by the three-point function. So both scenarios seem to coexist in this landscape, and there are actually a whole plethora of transitions that I will not go into, but I mean, you have many parameters, so you can tune them and study really geometrical properties of this random function. But to conclude, let me just try to extract a picture from this for our activity dynamics. So this is a model where you can actually identify a critical energy. It's an energy curve, epsilon star, which allows us to identify which of these, or when each of these two scenarios is realized. So the idea is that I start from S0, I decide that I jump to some energy epsilon 1, and if this energy satisfies this condition, and then the energy of the second jump satisfies this condition, then I can show that this inequality is met, and therefore the jumps has correlations between the different transition rate. And on the other hand, if these conditions are not satisfied, I am in this memoryless scenario, and this is actually what happens most of the times in these toy models. In particular, it is what happens, I've finished. If you focus on the transition path where essentially your energy does not increase, but you always jump to metastable states which have your energy or have lower energy. So these are what we call escape path, in the sense that they are really paths that allow you to decorrelate because you leave a minimum and you go down in energy, and likely you will never go back in your dynamics with subsequent jumps. Okay, so this really concludes what I wanted to say. So I wanted to give you an idea, first of all, of why this toy model, which looks very abstract, it's actually quite connected to the physics of Glassy systems. We understand a lot about relaxational dynamics because mean field is enough to understand relaxational dynamics. We do not understand much about activity dynamics because we have to go beyond mean field. And here we try to say something about this using knowledge which comes from, let's say, the statistics of the distribution of our metastable states. And I'm done. So thanks a lot for the attention.
So I wanted to ask about this onset of avalanche-like dynamics. So is the statement that somehow the 3-point complexity, as you're saying, is a better characteristic and you don't need, let's say, to go to 4 points and so on? Is there a...
No, not quite. So if you...
So is there a hierarchy of inequalities?
Exactly. And this is all controlled by the energies of the configuration that I have. So if I satisfy this condition for the first two jumps, this is telling me that the rate of the second jump is correlated to the rate of the first. And then I do a further jump, and I have the corresponding conditions. And then if I met the corresponding condition, I have correlations which propagate. So there, I would need to compute a higher point complexity.
But you see that in your models, you don't need to, that somehow an independent characterization of when avalanche-like dynamics sets in versus this 3-point complexity landscape. You're saying it always coincides? Is that
no, I would say my static analysis, if you want, is telling me hints, because we did some assumption behind this, about whether I do need to compute higher order correlations or not. And in most of the cases, I see that in fact I don't, because the 2-point function is enough to describe also correlations between 3 points. But if I decide to jump, so this happens essentially when I'm in a metastable state at low energy and I decide to jump up, and then I stay high in the energy landscape, then their correlations matter. But if I decide to jump at least at the same energy that I have or lower, then the 2-point function, if you want, is enough.
Okay.
And these are the protocols that people use. So equal energy path are the protocols that people use to study avalanches in finite D. So this points toward the fact that those type of avalanches in finite D, you don't have them in this type of abstract model.
Okay, thank you.
Thanks, very interesting. Just a question about the glass transition temperature in this model. Does that distinguish between the kind of minimas that you are populating at different temperatures?
It depends on which one.
In the p-spin model that you're calculating?
Yes, so you're referring to the dynamical or
yes.
the
dynamical glass transition, yeah.
Yes, it is, in the sense that at the energies which are of equilibrium at high temperature, what happens is that your landscape does not have metastable states. It just has saddles which are not trapping for your dynamics.
But what would it mean for the two types of minima that you are looking at for the dynamical glass transition? So you have two different types of minima, right? Avalanche and memoryless.
Yes, it's not the type of, I mean, it's more related to correlation between minima, but okay, to answer your question, we are down here.
Okay.
We are inside what dynamically you would call the glass phase, and there
I see, okay. It's inside the min, okay.
So that's, okay. The two scenarios don't tell you anything about
Understood,
TD,
understood.
You are below TD.
Okay,